Good afternoon. Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into lecture 151 and 152. So we will continue with free energy versus composition and activity versus composition diagrams for the binary system AB. Last class we have completed the binary system, Eutectic system, having a limited solubility in the solid state and complete solubility in the liquid state. This we discussed last day and we have completed it, but one point, actually some missed out points, actually I will first mention, cover them, then I will take up today's diagram. Today's diagram will be this diagram, Eutectic diagram with a compound, intermediate compound formation. So these are the three corresponding figures, like this is the phase diagram, this is the free energy versus composition diagram, and then you have the activity versus composition diagram. So our job is today, just first let me cover the this one. This is actually called this missed out. So first I take up points missed out in the last class. In the last class, points missed out in the last class, that is actually this is the figure, it was actually 2b, which is free energy versus composition diagram. Free energy versus composition diagram. This is last base. This one missed out points. So one by one, quickly finish this part. Okay, and then I shall take up the fresh topic, the new topic. That is in fact the last topic. See, okay, see that is this topic. So finish this part. One missed out one. So just please refer to figure this figure 2b, last day's class. Last day's class, figure 2b. I cannot draw them, okay, today. So this is already drawn. So please refer to that figure and just follow what I am saying. So what is this? In the composition range, this is the first point. In the composition range, 0 to A, G alpha curve, G alpha curve lies below the G liquid curve. Hence, alpha is the stable phase. So since the single phase, there is no intersection, no crossover, so just the one which lies below will be the stable phase compared to the one which actually lies above. Okay, so that is which is higher will be unstable, and the which one is lower will be stable. This has happened. This actually I have mentioned here. Second is the upper curve and lower curve. We may call this. Actually, lower curve will be the stable phase. So this follows actually the principle of second law of thermodynamics. That is, delta G is negative. Here I tell you, here today also it will come in a discussion. So that is when this curve has lower, another is upper, means their conversion actually from upper to lower is delta G is negative, from lower free energy minus higher free energy, so negative. And if delta G negative, that means this is a spontaneous conversion. So lower will be, upper one will be spontaneously convert into lower. So you follow certain fixed principle, then you will understand. Some don't say actually it is the lowest curve, minimum curve. Okay, what is it? Minimum? If you want to apply the concept of free energy minimization, you should apply it properly. That is the equilibrium state. Okay, is under the condition DGPT. DGPT is, I am writing here, DGPT is 0. This gives GPT is minimum. GPT is minimum. This under constant pressure, constant temperature, and free energy will be minimum. Minimum means this type of deal. This type of deal. This is minimum. GPT. This is for chemical reaction. A goes to B. A plus 2B goes to 3C. This is minimum. This is equilibrium state. Minimum, and this is the equilibrium state. So we have to apply properly this PT constant, GPT. Don't say this is minimum. Minimum, the word, the phrase minimum doesn't apply. What alternatively, what DGPT is 0, this leads to another one is what? Another is delta G is 0. Or delta G negative. Negative is spontaneous. So here delta G is this is applied. Delta G is negative. Which I am applying? It is not minimum. The minimum this type of deal. Lot of options are there of this composition gives rise to the minimum free energy of the system. Minimum free energy. This type of figure. These compositions are, this is equilibrium state, maybe say 60% C and 30% A, and okay, this 1:2, 10%, 20%, 10% A, 20% B, and 20, 30 and 70%. Okay, C. Then that may be the equilibrium state. Such examples, such situation of this is. Is it like that? That was this. This is no. This one is here, another is here. This is which curve? Alpha. This is the liquid. Is minimum this type of deal. So what is the criterion? Two criterions, remember, or equilibrium. One is delta G is 0, or this. This is actually often applied in case of what is computational thermodynamics. You can apply computational, you can apply free energy of the system, you can apply this. This is also possible, this is also possible. This is actually used, delta G0 is minus RT and such things. But anyway, delta G is 0. Then question comes, then what are other options? When the reaction is non-equilibrium, delta G is negative. The reaction will occur. Here also, at this point, it is not minimum. So actually, the slope gives you delta G. dg prime dn, the slope is delta G. That is negative. Means here spontaneously occur. So system is not equilibrium. So it will come down, down, equilibrium. When free energy will be minimized. For to apply minimization, this type of situations must be there in the system. For number of possibilities, number of composition possibilities, you have only one which causes the system to achieve minimum free energy will be the equilibrium state. The other configuration will not this, not that. Okay. It can be here also. It can be here also. Minimum can be here also. Here also. Depends upon actually in equilibrium constant. Delta G0 is minus RT. So many things. So don't mix up. Don't use the word here, phrase here that it is minimum. See, this is minimum of this. No, minimum is not like this. Minimum will give rise to a minima, curve minima, one. But here to the liquid, and so this is common tangent here in this segment. This is say liquid. This is alpha. So alpha is the stable phase, and in this there is intersection here. There is a common tangent. Liquid plus alpha. So here alpha, liquid plus alpha. This is again from the partial concept of equilibrium. From this comes delta G is 0, Gi bar, liquid is Gi bar alpha. This is called phase equilibrium. Apply phase equilibrium with this criteria for equilibrium. Equilibrium means either this or this. This or this, what you are using. When this type of figure you want, a minimization. Or if you use this, delta G is 0, is actually, then you have this two phase coexist, delta G is 0. Or another is what? And this one, delta G is negative. This is the case. Negative means liquid will continuously pass onto the alpha phase. Here, if you consider liquid to alpha, delta G is negative. Hence alpha will be the stable phase. Hence alpha the stable or equilibrium phase. Delta G is negative. Complete forever. Under this condition, you cannot have liquid. So above the melting point of a substance, of a species, above the melting point, liquid will be stable. Liquid has lower free energy than the solid. Liquid has lower free energy than the solid. So that means delta G. So above melting point, I solid goes to I liquid. Above melting point, delta G is negative. Here equilibrium, these two will not coexist above melting point. So delta G is negative. You have to use this. It's a negative. Delta G is negative. Below, free energy is below. Negative means Gi liquid has less free energy than Gi solid. I is iron, say, water, say, zinc, say. So less than above melting point. Below melting point. So here delta G is negative. Delta G is negative. So what is happening? This process is spontaneous. So let it be so spontaneous. It occurs until solid disappears. So liquid will be the stable phase. And when they coexist, that is delta G is 0. That is when at melting point. At melting point, delta G is 0. That is Gi liquid is Gi solid at melting point. Okay. So this is actually this happens. So be careful about this. So this is based on the principle of delta G is negative. So spontaneous and equilibrium phase. But it is not minimum. This is actually wrong use of the concept. Lower is stable like this. Okay, no, this is actually this reason. And okay, this I'll take up this today once more. So be careful about these errors. Okay, don't use this. Just use, remember this delta G negative. So liquid will convert into alpha. Equilibrium does not mean that they have to be together. They have to coexist. No. Single phase equilibrium. One is not stable. One will not be present. Will disappear in favor of the other. For example, M solid plus O2 gas. So I told you the concept of equilibrium is very important. 4 different issues that have made thermodynamics a difficult subject. I discuss this for number of lectures, 4 issues. One of them is equilibrium. Many books have also said, I have seen, that it is since it is minimum 1. Minimum is what? Why I am using minimum? G minimum is under constant pressure, temperature, and curve would be, that should be curve, a minimum curve. For many different composition options, one option. M plus O2 is MO2. It does. Suppose PO2 equilibrium, I am giving you, I am just discussing, say 0.03 atmosphere at temperature, say T1 from delta G0. This will give you. Delta G0 gives you. So what happens? So equilibrium, how will you use the equilibrium? So equilibrium, this language, equilibrium, the phrase equilibrium you use where? Many possibilities. At T is T1, PO2 is 0.03 atmosphere. What is the equilibrium state? This is the equilibrium state. The whole reaction is equilibrium, means M, who are present? M solid, O2 gas under this pressure, and MO2 solid are in equilibrium. This is 1. First option, first 1. Again, at T is T1, maintaining that, because I have the data for that temperature, so stick to that temperature T1. PO2 I am increasing, say 0.05 atmosphere. Then what will happen if we maintain this? So that is cylinder piston arrangement. This I am not saying. If we maintain this, then what will happen? So continuous forward reaction, delta G is negative. Here delta G, you can write here, delta G is 0. So there will be equilibrium. Now at P is PO2 point is, so delta G will be what? In the forward direction, in this direction. I'm starting in this direction, delta G is negative, because metal will try to oxidize and trying to reduce this value 0.05 to 0.03. So continuous this occurs. If you maintain this, metal will oxidize. If it's continuous maintenance, it should be actually here by cylinder piston arrangement or continuous flow. So continuous, you maintain. Just once, no, that will not work. Then it will reduce, come back to this. For some time it will be negative, then come to this. So what is the equilibrium here? Again, delta G is negative. Then what is the equilibrium? Delta G is negative. And equilibrium state would be what? So metal will react and continuously disappear. Ultimately it will be fully eliminated. because I forcibly maintain this one. So what is the equilibrium state? MO2 solid as well as oxygen gas. This is equilibrium state. Not 3 anymore. This is also equilibrium. This I will show you actually in the stability diagram construction when I discuss Gibbs phase rule. And again say, again third case, what you say at T, again don't change the temperature since Q2 is what? 0.01 atmosphere. So initially you have actually all these three. Then what will happen? This will work actually since MO2 will dissociate back into this direction. Try to increase the PO2 pressure to 0.03 by releasing some oxygen this way, producing oxygen. So what will happen? And if we maintain the MO2 continuously this way, delta G is not zero. Delta G is what? In this case, delta G is positive. So positive for the forward direction. Yeah, for forward. So forward reaction will not occur. But suppose you have MO2, so forward direction, forward direction. But for the same reason, delta G is negative for the reverse direction, backward direction. And delta G is negative for the backward direction. So what will happen? So MO2 backward direction means MO2 will convert into M plus O2. So what is the equilibrium phase? Delta G is positive or reverse direction negative. So this will happen. So what is the equilibrium phase? Equilibrium phase will be what? MO2 will disappear. What will you have? M solid equilibrium state. M solid and oxygen gas. Because oxygen gas you have maintained, 0.01 is maintained, underline. You maintain, that is your lookout, your responsibility. How to maintain? If a constant pressure, maintain. Or continuous flow. So then we have this. So this is one possibility of equilibrium. This is another possibility of equilibrium. And this is still another. This you can get from easily. So suppose if you try it in a closed system also, if you have 0.0, start with 0.05, but not maintain. Don't maintain point. Just start with 0.05, then it is reduce, 0.04, 0.035. Then the moment it is 0.035, it stops, and these are all three phases. All three phases are in equilibrium. And this condition is, equilibrium condition is achieved in the system. That is also equilibrium. So equilibrium actually, see here which principle we are using? Delta G is 0, or under this condition, when this equilibrium is attained, delta G is 0. I have written here. Or delta G is negative. Through delta G is negative, you can achieve an equilibrium state. Delta G is negative spontaneous. As a good example, this one. Delta G negative. That's why equilibrium means what here? A spontaneous reaction leading to elimination of a phase. Which phase here? Metal phase. So then MO2 and oxygen. When I discuss phase rule, I will further clarify this. But remember, Gibbs phase rule, then I will discuss, rediscuss this or further clarify this. This is the thing. So equilibrium, the single phase, the whole phase diagram is actually here. Here, liquid is equilibrium. This whole diagram is equilibrium. Doesn't have to be liquid plus alpha all the time. Here actually see liquid like this, okay? See, liquid alone can be, alone. The whole diagram is equilibrium diagram. Depending upon situation, you have one phase, two phase, three phase, like this. So be careful about the term equilibrium and use of minimum and such. Remember, two things you have at your disposal in your armory, in your actually weapon. delta G is negative, say delta G is 0, say delta G is 0 for equilibrium, or G under constant pressure and temperature is minimum. And what is the type that one? Now constant pressure is minimum, G is minimum. Actually, this is actually minimum. Under constant pressure and temperature, that I said, I showed you. That is actually at the minimum it will attain. There you use minimum. When you have a number of composition options of this, only one composition, one particular composition we call equilibrium composition. When that is attained, then the system will come to equilibrium and no more reaction. Before the reaction takes place. Okay, this. Okay, this is actually, we should note this. Okay. This again, I see, I tell you what, since I discussed this, I remove this, I remove this. I'll take up. So be careful about of the phrase minimum, equilibrium, and use of minimum. So don't use here don't say it is minimum here. Yeah, because you see lower means delta G is negative applying here, and one will be eliminated to the direction of decreasing free energy. That's it. You will have one, not both of them. Possible. One phase equilibrium possible. Okay. Another thing is this. Okay. So this actually this one. Okay. Well, it is better actually. I avoid this time, and then it will actually consume much time, eat up our time, and we'll be lagging behind towards the end. So let us give the conditions. Second one is what? Let us discuss this. Okay. So lower. Okay. In the composition range, this is first one, 0 to 8, last day's class, figure 2b, underline. This you refer. If you don't refer, this you will not understand. That figure and today's discussion. Quickly. In the composition range, sequential I consider 0 to A, A to B, last day, B to C, C to D, and D to 1. These are the segments. And which is stable and why stable? Which are the equilibrium phase and why? This part I forgot. I'm sorry that I forgot last time. Also, I didn't have time. I forgot, so today I'm making up. So, in the composition range, A, B now, 0 to A to B, next segment. In the composition A, B, common tangent, this time common tangent. A common tangent the moment common tangent you understand what? Phase mixture. Two phase. The curve to the two phases, a tangent is drawn which serves as common tangent for both the curves, and the composition range over at which this occurs is the composition domain over which two phases coexist. Okay, you know, this I said a common tangent is drawn between the two curves G alpha curve and G liquid curve. Okay, G alpha curve and G liquid curve. Hence the two phases alpha and liquid coexist. Actually, in the form of alpha plus L. Okay, third. you get passing from this, the third point. So alpha, then alpha plus L, last bit. Third point is quickly, in the composition range, B to C, GL is the lowest curve. GL is the lowest curve. Lowest curve is not minimum, no, here. Lowest means you consider any two, delta G is negative. Then take up the stable one and the other one, third one. Again delta G negative. And still another one. Like that was actually alpha solid solution, beta too. So it is alpha, beta, and below it is the lowest. It's the lowest of them. Means compared to any two, and conversion occurs. Like liquid alpha. Similarly, so liquid alpha first, G alpha. Oh, liquid is lower. Free energy, lower position, and smaller free energy. So G alpha is stable. Now compare with the, again next take up the G beta. And it is again here same thing occurs, that this is liquid is lower. So two at a time, as it. Two at a time. See delta G is negative. Of this and this, delta G, G2 minus G1. Liquid to alpha or liquid to beta, like this. Each case delta G is negative. So that's why I have used the lowest. Don't randomly use minimum. Minimization of free energy, so everyone is saying. Saying just a minimum free energy, so it is equilibrium. And no more statement, no more explanation. So what is equilibrium? Sir, minimum free. What is equilibrium state? Minimum free energy. They don't ever use that. How do you get this? From DG under constant pressure temperature, DG prime rather. DG prime PT is 0. Hence it is minimum. We know actually DG prime PT that can be modified into DG prime PT by dN. N is the number of moles actually that is being transformed during the process. In progressively changing N. So DG prime PT by dN is 0. The moment dy dx is 0, y is minimum. This is the formation of minima. Minima doesn't mean so here upper lower doesn't use the term minima. There delta G is negative. G is the lowest, so I am using lowest, I don't use the minimum. Actually, lowest means you consider any two, you will see the lower one will survive. Then consider now next this one which survives and the other third phase. Again see which survives. So G liquid is the lowest curve. G, you have to be very careful about this point. That application of the phase minimum while you are considering the equilibrium state. Okay. So I'm sorry, GL is the lowest curve. Hence as the liquid, hence liquid is the stable phase. Hence liquid is the stable phase. So refer to the diagram. So we are moving from first extreme left alpha, then alpha plus liquid, then liquid alone, and liquid alone is the stable. Liquid alone. You write alone. Then what you get next? Guess liquid plus beta, and finally only beta. If that occurs. Okay, let us see. Fourth. I don't have the diagram. Just I have to hinting. I have to hint you at that diagram, but you can easily get back to that video and you will get this. Fourth is what we're almost done. Fourth point is in the composition range. In the composition range again. In the composition range, C to B to C, C to D, in the composition C to D, a common tangent, a common tangent means curves have intersected. That's why common question of common tangent comes. Around that intersection points, one concentration is less than that intersection point, and another concentration is greater than that. Common tangent. This is the characteristics of the common tangent. And principle is partial molar finite. Phase equilibrium. Gi bar alpha. Partial molar finite, how to get? From the integral molar that I am drawing, today also I am drawing, that integral molar, this is integral molar, tangent, tangential intercept. That will be compatible with the equation, mathematical equation of partial from integral, in the form of derivative also. That's why tangent comes. So this was discussed, clear, everything was made clear. So that's why tangent. And common tangent means when you have actually two-phase mixture. Okay, for single phase, to get the partials, draw a tangent at the composition or point under study of your choice. Then you will get how to get the partial molar finality from integral molar finality. This is simple part. But common means when two phases are actually under study and possibility of their coexistence is being examined. In the composition in CD, a common tangent is drawn between the two curves. What are the curves? Between the two curves, G liquid and obviously G beta comes into picture now. GL and G beta. Common tangent is drawn between these two phases curves. Hence, since common tangent is there, hence the phases which are this liquid and beta coexist. Which form you get in the diagram? Liquid plus beta. And here liquid and alpha coexist. Alpha plus liquid. Fifth is last point in the composition range. D1, okay, D1, G beta curve lies below the G alpha curve, G liquid curve, GL curve. I'm very sorry, GL curve. Hence, beta to alpha will be spontaneous. So, liquid to beta spontaneous. So, beta will finally survive or will be finally found or will be finally stable. Will be the equilibrium state. Will finally obtain. Okay. So below, so liquid continuously converts into beta. So hence, the phase beta is the stable one. Hence the phase beta is the stable one. That's it. These 5 points I missed last class. Okay. So please refer to figure 2B last video. Then you will get this. Okay. This is the last class means lecture 150 and 149 and 150 lecture. Figure 2 last class. Last class is what? Lecture 149, 150. Please take care. Thank you. So this is actually the one that I made up. So next job is today's. So let me remove this. Let me remove this. Let me remove this. Today's agenda, today's topic, today's class. Actually, effectively today's class begins now. What is this? This is actually third system that we are discussing. That's why figure 3. See, all of them 3. Third is what? Eutectic system. Eutectic system with intermediate chemical compound formation. Formation. That's it. This is the third one. Okay. Now about this, I tell you before I write down anything. Let me explain you the summary of this. Okay, you follow with me what I have done. The similar thing I have done. Similar because I don't want change. I should not change the principle. I should not actually get drifted from what I said, what I had said before. Should not violate what I said before. Okay, so say consistent thing. Then you will have confidence. What is this? First of all, this is the phase diagram. This is the phase diagram we are talking about. See, this is your intermediate compound is what you see. This is XB x-axis 0 to 1 as it should be. Binary A this end and the other end B. But a compound forms. The name of the compound is chemical compound. Stoichiometry is a stoichiometric compound. Means there is no non-stoichiometry. Perfect. What is the AB2? And what is the what composition? This XB is how much here? AB2 means B is XB is what? 2 over 3. 2 over 2 plus 1 means 3. 2/3 at 0.6. So this is the location. When XB is 2/3, this corresponds to the compound AB2. This is the x-axis. Y-axis temperature as it should be. Oh, I forgot to write. I am sorry. I should have not. I may forget. Temperature, I forgot actually. Temperature axis. So no problem. So I have marked off the melting point of A here, melting point of B there. Liquid phase is actually completely miscible. A and B completely miscible in liquid phase, liquid state. And this solution, liquid solution, is considered to be an ideal solution. That's for simplicity or say for convenience or just consideration. Unnecessarily we should not complicate this, okay? Because we have already complications at other places in the solid state. This is a complicated thing. So liquid solution is ideal. This is considered. What else I will tell you? This is first is this line compound they say, this vertical line. This is the AB2 line. So you see here liquid plus A, and this is a kind of eutectic diagram between what and what? A and AB2. this one, this half. It is not half actually, this part, a eutectic, and the other side is another eutectic diagram between AB2 and B. So two eutectic acid are actually in operation around the compound AB2, line compound AB2. Okay, this is the diagram. What we have to do, again same thing, draw the free energy composition diagram and activity versus composition diagram. Free energy versus composition. Why? Actually, what is the rationale behind this phase diagram? Who will explain this phase diagram? Why this happens? From the free energy composition diagram. Free energy will dictate which phase will be stable, which regime. So this explains this phase diagram, justifies this phase diagram. This consideration of this results in this phase diagram. Phase diagram is actually an equilibrium diagram, and we are applying the concept of equilibrium here. So anyway, so again you see integral molar free energy is plotted against xp as usual, and what you have seen. Remember what is important here, I told you the same principle, G liquid. One is G liquid, another is G solid solution. Liquid means liquid solution, you understand that. Liquid solution and solid solution. But unfortunately this time no solid solution. It is totally immiscible. A and B totally immiscible. No solution. No alpha, no beta. Instead, there is actually strong negative deviation from ideality so that a compound formation takes place. So anyway, no solution. So we have to work with pure A and pure B. So only G liquid will be constructed. G liquid curve. How construction? Again repeat what is stated. Delta Gm plus G unmixed. Liquid means pure A, pure B unmixed. So let us place the free energies. So what we will place here, see the temperature T1, see it is below the melting point of A but above the melting point of B. Now you see. So since it is below the melting point of A, that means at this temperature of T1, solid A is stable and solid A has lower free energy than the liquid A. So the one which is lower will assign a value of 0. Hence A solid, this is A solid. See please, A solid is assigned a value of 0. What? Integral molar free energy means free energy is giving a value of 0. Okay? It's okay. It's okay. It's okay. Yeah, okay. So what this I am saying. So assigned as A solid has the free energy of 0. And what else other side which will be, this is above the melting point of B. So liquid is a stable state above the melting point. So liquid B is the stable state. So liquid B has lower free energy than the solid. So let the free energy of liquid B is be 0 and 0 has been. Okay. Now about since liquid will handle, so A solid free energy is 0 here, A solid, and you have a free energy of A liquid is greater than that. So I have placed here. Yeah, this can be exactly, I told you there is some relation, thermodynamic relation, how to get this from the values of enthalpy of melting and melting point. This is the simplest way to find this. But anyway, suppose this is the point. So this is the GA0 liquid. Now get the unmixed liquid. Connect this A liquid and B liquid unmixed. What is the delta Gm? Since liquid solution is said to be an ideal solution, so delta Gm ideal is what? RT XLn XA plus XPln XP, you know this. So combine this curve and this curve graphically. The moment you combine, you have this G liquid curve. See, combination of this and this. See, follow slowly. Go this way. This way. I repeat. This. Go on. Here to here. These are tangents. Don't worry. So this the curve G liquid, and the then I will discuss actually. You have to take common tangents. This I will discuss actually later on. While I keep on writing, I will explain this. But this is the main thing. So here see, for example, liquid plus A. So what is coexistence? Common tangent. Between whom and whom? Between whom and whom? Now one is liquid. So Gl is there. Between Gl car and which one? A. Pure A. No alpha. Not G alpha car. Or for that matter, G beta car. Or A. So common tangent. Here it is drawn. See, this is the car Gl. Concentrate on the Gl car, and this is the A solid, pure A solid, this point. So this and this is a common tangent, and this is this composition range. So between 0 and call this A, 0 to A, you have actually, this is A, liquid plus A. After that, you have actually, see, this I am not discussing. Then what you have? Activity versus composition diagram. Okay. So activity versus composition diagram. Okay, here actually I tell you what, this I will explain you. This vertical line I have given name Mn corresponding to the compound Ab2. What is the height of the Mn? I have given here. This is very important. How I found this value of the formation of Ab2. Actually, I would say okay, 2/3. What is that called? 1/3 Ab2. 1/3 Ab2. This I will discuss. This value, how to find this? This is a little bit elaborate. This is a little bit involved. So, but I will explain. But this vertical line is very important. This is a construction line. So, what are the construction line? Final important lines or crucial lines are what are these? G liquid as usual. Pure this end A, the other end B solid actually. B solid I have there is no existence of B solid actually, so B solid I have not actually given you here. A solid, liquid, and another is this vertical line, that is for AB2. AB2, yeah, vertical line corresponding to vertical line. Point C, remember. Point C, vertical line hits the x-axis at C, corresponding to composition C. ABCs are composition in terms of XP. So this is an activity composition. I tell you what. You see, when you have this temperature T1, remember. See, again I have forgotten. We have to write T is T1. T is T1. I should write. I'm sorry, but I have to write here. T is T1. Like here. For this T is T1. Here also. This diagram for T is T1. As it should be, because about T1 we are discussing. Okay, only one temperature we will consider because that typifies the other temperatures. Okay, all temperatures, and in fact we have considered a complicated situation by considering temperature T1 because many phases are involved here. Anyway, so T1. So what is the activity? I tell you. See here. I tell you what. Here, see, liquid plus A, liquid. So you draw as usual. Today you should note this. We are plotting AB liquid on the y-axis, this y-axis, against XB as usual. And the other side is not AB solid, unlike last time. It is today AA liquid. That is very good variation. So you understand how well you can draw AA also, activity of A. You can draw also. So this will move from this side to that side. And as it moves from this side to this side with increasing XB, this side to this side, increasing activity. And here also activity A will increase from this side to this side. So XB moving this direction, XA is moving the other direction. When XB is 0, XA is 1. When XB is 1, XA is 0. So it moves from 0 to the other side. Okay, this is very easy. XA is 1 minus XB. So that is not it. One thing I tell you, first of all, you connect 0 connect this line. Now X A is X line. How connect? You connect this 0 and 1. Connect this. This is A is X line. When XA is 1, XB say AB is XB line. When XB is 1, AB is what? AB is what? 1 here. Okay, AB, I'm sorry, AB 1 here. 1, AB is XB. So just connect this corner, diagonal. Connect and also connect this. This will help you immensely because the moment liquid phase will be coming into picture, will be encountered, liquid phase will be come across, then in the liquid phase, liquid phase is a solution, ideal solution. Liquid is an ideal solution. So for ideal solution means they will fall on the ABXP line. So clearly you see how the whole diagram very easily you can draw. See the concentrate on this liquid and this liquid. This you can draw. Given that liquid solution is an ideal solution, and very easily. How? Just say AB I am showing. AB liquid. AB liquid is what? Again, like last day, activity of B with respect to pure liquid B as can understand. And I am telling you activity A liquid today, activity of A with respect to pure liquid A as can understand. Concentrate on B, only this. If you understand. So what I am suggesting, draw a diagonal, connect 0 to 1. As you have already seen, draw that is AB is XP. AB is XP, just connect this 0 to 1. AB is XP by dotted line maybe initially. So you see what you will do. See, follow how drawing this simple thing you can draw activity versus composition in this type of situations. Or let us say, you concentrate. Please concentrate the liquid domain. It is a liquid. A to B. See, A to B is liquid. Here, A to B. What it will do? AB is what? Since ideal solution, AB is XP. That means it will fall on the AB is XP line. So this is the curve. This for this segment. You have started from the middle, not at the end, but you will reach up to the end on either side, either extremes. Follow here. Clear? This segment, I have given name QR. Then what will do? Then you come across outside this AB, outside this on the right hand side or left hand side, two phase mixture. What is it? On left hand side is liquid plus A, and the other side is liquid plus. This is actually, if you know this diagram, AB2. Please read this. Yeah, please read liquid plus AB2. This is the compound AB2 as it should be. This is liquid plus AB2. The compound AB2 is separated on either side. Is bordered on either side by liquid plus AB2, liquid plus AB2. This is actually very easy to follow. So liquid plus AB2 on either side of AB2. Okay. So you can read easily. This is AB2 I have already written. This line, concentrate this line compound they call. Line compound or chemical compound, stoichiometric compound. When there is a strong negative deviation between A and B in the solid state. So that electronegativity difference is such that they tend to form compound. Sodium and chlorine, sodium chloride. Like this, okay? Manganese and sulfur, MnS, like this, okay? So compound formation. So sometimes it's non-stoichiometric compound, but let us consider today it is stoichiometric compound. So there are only one. If it is a non-stoichiometric compound, then there is certain range, solubility range, and it will be actually not like this, okay? It will be like this actually. Say intermediate phase we call it then. Intermediate phase, and we have this type of situations, not compound. So gamma, intermediate gamma phase. So gradually decrease the range. This is the composition range. Gradually decrease, then it will finally eventually become a line compound when there is no solubility range. So purely means there is no variation in composition in this phase. So it is rigid composition. So what is the composition here? 2/3 XB. So this is about AB2. So concentrate on this. So you see, I repeat, I come back to this one. So complete this. On either side of this, On either side of this liquid phase, you have one is liquid plus Ab2 phase mixture. On the left hand side is liquid plus F. So when there is a phase mixture, what I told you last class, two phase mixture means horizontal line. Horizontal line. So draw a horizontal line this side and other side. Two phase mixture. Why activity doesn't change anymore? This is a y-axis doesn't change. Horizontal means activity does not change. Why activity does not change? Because composition of does not change in the two phase mixture. Composition are tied to this. This I said. So for this I explained. Okay, lengthy explanation I offered. So this is these two. Okay. So you have already drawn up to this point. This I'm like P Q R S over. Then you stop. Then come to the other side. Okay, let us see. Stop. You are stopped here. What is this? This side is what? D1, which is liquid phase. Again, liquid means ideal solution. So D1, this segment. Go to this segment here. D21. So go here and here. Ideal solution, liquid. So falls on the AB's XB line. Oh, I'm sorry. This I should not. AB's XB line very important. I have to be very careful. It's okay. I have to be very careful. Okay, I should not actually, anyway, it will take time then. Okay, to fix it. Okay. So it falls here. Then what happens on this side? Then what you have again? It enters into here. Let's remove this distraction. Remove this. Enter two phase mixture. What is that? Liquid plus Ab2. So since two phase mixture, what it will be? So what is the name of this? Bu, and then horizontal Ut, Tu. So this. So stop here. You have already stopped where? S. Joined by vertical line. S T. Enter curve is what? P Q R S T U D. That is for activity of B liquid, this y-axis versus XB curve. Similarly, you can draw this time A activity of liquid. Similarly. Okay. What you will do again? You see again same deal for the same temper, same everything. So what you will do is this. Again, you see here, consider this A to B falls on the, what is this line this time? This corner 0 to 1, to consider 0. Actually, it is actually here this to 0 to 1. Actually, this coordinate is 1 1. This is 1 and that is 1 1. This is 0 0 1 1. You know, activity is multiplication. Everyone can draw. Okay, this is y is x. Just asking to draw y is x curve. You can draw y is x curve. Y is x curve is what? Y is x curve means 45 degree angle also you can consider. Y is x. Y is x. This is the y is x curve. So everyone knows this. So this is. So here also A is x line again. So connect this point and this point. And now concentrate on the liquid phase. On the liquid phase, first of all, A to B means this domain you have this line. This falls on this. A. What is the equation? What is the name of this line? Now A is x. This was what is the name? AB is xb. A x, and we are interested in A liquid. So A is x, this segment, and then again outside this two phase horizontal. Out beyond this part horizontal. Stop there. Then come to the other side. Come to this side. This side, what is the value of A? This is P or B. The activity of B is 1. XB is 1. XA is 0. Activity of A is 0. Start from 0. And this D1 segment, D1, so it falls on the red line. So start from 0 here. You have stopped here. Again, then entered in the two phase region, horizontal. So you have stopped here and already stopped there S prime and call this T prime. S prime is stopped, T prime now stop. Vertical line. Vertical line always for compound formation. Vertical line. So we have all these both activities are explained. So you have to get this, okay? So I have written here what is the name of this. Since it is P, Q, so I have given this name P prime, Q prime. This is actually Xa is what, how much here? I start from Xa is 1 here, 1 as it. You can, other way you can work also. So P prime, Q prime, R prime. Where is R? R prime. S prime is where? Here S prime. Then T prime, U prime, D prime. This is in nutshell what is going to come, but more explanation will maybe required, and I will keep on explaining this. In case particularly here about the common tangent, I will discuss, okay, in the free energy composition segment. Okay, so let us keep on. I don't have much time actually. Time is, yes, I have time, but I have enough many things to write actually. I don't have. So the phase diagram, I have many things to actually explain. So I may actually have some shortage of time, but let us see what happens. The phase diagram for the system that I mentioned at the top, for the system is shown in figure 3a. The liquid solution is considered to be an ideal solution. To be an ideal one. Okay. An intermediate stoichiometric compound compound AB2, name of the compound is what? It is like a chemical compound. Okay. Okay. So you'll see the intermediate compound you will come across. Okay. So this, okay. So AB2 occurs at it is actually, you know yourself, 2/3. You know this because how much 2 atoms of B and 1 atom of A. What is the atom fraction or mole fraction? 2/3. So at least this 2/3. The diagram can be considered to be comprised of two eutectic systems. What are they? One is A plus AB2, another is AB2 plus B. A plus AB2 and AB2 plus B. Demarcated by the line compound compound. What is the name of the line compound? Means the AB2 compound that we are considering, AB2. So we wish to draw the free energy versus composition actually I tell you what, very interesting. We first draw this, then we draw this. First draw the phase diagram, then draw the activity versus composition. But this phase diagram is a consequence of this study. So this precedes that. As if you actually free energy, these curves you are experimentally drawing. You experimentally draws, okay? Experimentally, and then you see this actually. Then from this you infer that these are the equilibrium phases at different compositions, at different temperatures, like this, okay? So anyway, but when we try to learn this, we first draw the diagram, then draw the free energy versus composition. Actually, this is experimental. When you want to measure something, delta G is a measurable quantity, not G. You don't know, but delta G can be found as G if you have a reference. Okay, so suppose these are the reference values 0, 0. Refer to this delta G if you can find, and not difficult at all. So some delta G changes, delta GM say, delta G mixing say. The delta G mixing, refer to this will be the G of the solution. So delta GM experimental find, that will be treated as G liquid, okay? This, okay? Refer to these values, refer to this, with reference to these values, delta GM will be actually GL, actually this, okay? So, so for example, what is this? This actually you can get this, okay? So if you refer to this zeros, A solid and B liquid. So anyway, you don't, for the time you consider the easier approach, consider the easier thing, that is draw the phase diagram. What is the free energy versus composition diagram? Free energy versus composition situation. So this is actually, don't hit this one. Is okay? How much time left?
1 hour 12 minutes cut. 1 hour 30 minutes cut. Still
12 minutes now.
12 minutes.
Another 1 hour, 2 hours, 12 minutes we'll try. So we wish to draw the free energy versus composition, and you try this way, then you will see when you try to find out, when you determine, compute a phase diagram, or say you want to experimentally find a phase diagram. Say iron manganese system or iron silicon system. Then you have to do experiments. These are the experimental curves, experimental values. So from here you can come down here, from here you can go up there. And this is actually a consequence of these actually activities. These are intertwined, linked up. Where there is free energies, this is actually GI bar. What is how good activity GI bar minus this I told you how to find from this curve activity versus composition. This I said. Alternatively, the alternative, okay, one of the previous classes, okay, maybe 2 or 3 classes before, I said alternative way, draw a tangent, gi bar, and gi bar minus gi zero is RT ln AI. Gets the activity value. This I told you, okay. You recall that one. Huh? So, finality versus composition. This is actually one approach. Another is actual activities. This okay, activities directly you can get this from the activity. If it is ideal solution, you get this activity. Is mole fraction. And if it is non-ideal, then you must know the behavior of the solutions, the value of gamma. And gamma requires a model, solution model. So if it is regular solution, see like this. Okay. Gamma is actually you will require gamma to draw this. You know, you can qualitatively you can draw, but exact value you need to know the omega value. Okay, the regular solution parameter value. Okay, this. Anyway, these are actually different things actually. So what I say, these are one intertwined. Activity and partial molar free energies are intertwined. Ti bar of free energy say. So integral molar free energy to partial tangent. If you don't use that equations, okay, see, equation if you don't use, then tangent, partial. And once you know the partial, gi bar minus gi zero is RTL and AI. Okay, very good. And if it is ideal solution, you don't care at all. Who will go to that? Activity is mole fraction. And another thing I told you here, this thing I forgot. I may forget actually. P dash, let me write here. I do not know. I am actually taking this side, and there actually this will be less. This is activity of a liquid, obviously. Activity of this gentleman goes this. I follow me. Starting from 0, up, horizontal, up for the compound formation, then horizontal, then this, and it is almost to the pure A, and this. So when it is pure A, you see the activity has not been 1 with respect to liquid. Why? This is a very interesting question. Why activity of A when it is pure A is not 1? Is that it is pure liquid? Activity will be 1 if it is pure liquid. You are asking activity of A liquid. Means activity of A with respect to pure liquid as standard state. So when it will be 1, when it is pure liquid, is it pure liquid here? At this end, pure liquid? No, see the phase diagram? Oh, liquid down there. Here, A. This is A. This is the liquid composition, which doesn't change anymore because two-phase region liquid composition does not change. So no, it is not 1 here. It will be, this side is what? This is liquid composition, this is the pure solid. Solid activity will not be 1 with respect to liquid, pure liquid A as the standard state. Pure liquid A with respect to pure liquid A is 1. Pure solid A with respect to pure solid A. So it is not 1. What is this? I am talking about activity A liquid. Is 1. It is better you write this. It will be actually, you must note that activity of here, when activity of A with respect to pure solid, it is, suppose you don't consider liquid, solid at this point will be what? Since pure solid A is there, so it is 1. So activity of A solid is 1, and in this domain remains 1 because two-phase region, so no change in activity. So activity of A solid is 1, liquid will be less than that. Why? Because this temperature is such that below the melting point of A, as I have told, so solid has lower free energy. So with respect to solid, you have a higher value of activity. And with respect to higher free energy, like that is for liquid, you have a lower activity. I repeat. So activity with respect to solid is 1, and with respect to liquid will be less than 1 because solid has a lower free energy. With respect to a lower value, activity is greater than with respect to a higher value. So this is lower value. I am writing you here. Is actually his answer is e to the power minus. I don't talk too much. Minus delta G0 melting. This is M for melting A by RT. This I told you last class. Okay, remember, recall last class also I discussed this. In terms of activity of B, I told you. This is actually times activity of A solid. I'm giving you activity A of solid, and this is 1. In this domain, activity of A with respect to pure solid as a standard state is 1. This is the relation with one standard state and another standard state. Transfer of standard state, change of standard state. Very smart you have to be, very smart. So one you know, other you know through this, and this is the answer. But best answer is what? What is the activity of a liquid? Tell me, quick answer. Activity of a liquid here. A liquid is what? Is nothing but Xa liquid. Xa is how much? The Xa given by which point? This is A, composition A, that is Xb. X is 1 minus Xb. 1 minus A is what? Write this nicely. Is Xa liquid. Since as if you don't consider this, Xa liquid, what is that? See, A, B, C, D, we have from the very beginning, we have considered in terms of Xb. Xb is A, Xb is B, so that happens. So Xa will be 1 minus Xb. So what is this? 1 minus Xb. What is the name of this? For this composition, liquid is where? Liquid is A. Xb is A, 1 minus. So if you are asked, 1 minus A. And also in this context, you write, I have written here. I am writing once more, activity of solid is 1. So this part here at P. At where? At P prime. At P prime. At P prime. This is P prime at P prime. At point P prime. At that state. This is this actually. And again you see, very interesting. See what you see. You see it should be. It should be 1 minus A, as I said. So less than 1. And you see, less than 1. Delta G0 melting of A is what? Positive or negative? Below, this is below melting point, delta G0 melting will be positive. Liquid will not form. Will not melt, solid, okay? It will not melt, it will freeze, okay? It will freeze, okay? So what does it mean? Melting is not spontaneous. Solid to liquid is called melting. Melting is what? Solid to liquid. So delta G0 melting is below melting point is not possible. So delta G0 is positive. Delta G is positive or delta G is positive. That means liquid has more free energy than the solid. That's why solid is lower free energy. Solid is stable. A solid. So delta G0 melting is here. Of course, it is melting is not possible. It's positive. So a negative of a positive minus positive. Minus, that means it is minus. E to the power minus anything means less than 1. E to the power minus negative means it is less than 1. 1 minus A. A taken away from 1, less than 1. While A respect to solid is 1. So this is from the principle of change of standard state. Okay. So careful. See, A is solid. So it will spontaneously occur to you, sir, activity is 1. With respect to solid A as the standard state, but you have considered with respect to liquid as standard state. You have taken the advantage there, since liquid phase, in the liquid phase you have taken advantage, this segment AB, big segment, and D1 you have used, but you are free to use, that you play with. Sometimes, this is the first time that I will consider the activity of A. Previously, what I have considered activity of B liquid on one y-axis, and the parallel y-axis activity of B solid. See previous cases, you'll see. The third one. So careful about this. So to say these points I missed actually, but let me keep on writing. Okay. And we used to draw the Chmcl Compnd and the activity versus and activity versus and the activity versus composition diagrams. composition diagrams. We at temperature T is T1. At temperature T is T1. This is the job. As before, so proceed. How will proceed? As before, the GL curve. GL curve. GL curve, I told you here this figure, this GL curve, this I already explained. So GL curve is drawn by graphical combination of the delta GM ideal curve. Why I am considering ideal curve? Why? Because it is given that solution is ideal. If it is not ideal, then don't write. Don't consider acting this equation. RT XLN XA plus XP ln XP. No. What you write? XLN AA. Activity of A, which is the general one, original one. Ideal A and the XB intact. This XB, first XB intact. ln XB ln AB. This A becomes XA, AB becomes XB when it is ideal. So delta GM ideal, this time delta GM ideal works and ideal curve. And which curve? Mixing, unmixed, and G unmixed, and the G unmixed liquid curve. So like this, as you already write this, G liquid is nothing but mathematically, that is G liquid is nothing but delta GM ideal plus G unmixed liquid, unmixed liquid. Okay, this curve. Okay, you know this one. Liquid is what? Write this another line. RT X ln X plus XB ln XB plus what is unmixed is what? XA, I have written here, XA GA0 liquid plus XB GB0 liquid, because it is liquid unmixed. Okay, XA GA0, since I am considering liquid, G liquid, XA GA0 liquid plus XB GB0 liquid, you know. Okay, very good. Note in this context, the GA0 which I have assigned, remember I explained assigned GA0 solid is 0 because temperature T1 is below the melting point of A, and here GB0 liquid is 0 because temperature T1 is above the melting point of B. So in this context, the GA0 solid and GB0 liquid, see, changes, not G0 solid and GB0 solid. Neither GA0 liquid and GB0 liquid. No, it can change. This side is solid, other side is liquid. This is also possible. Okay, both possible. That is also possible. Depends upon the melting point and the temperature under melting points and the temperature under study. And GB0 liquid are both assigned a zero free energy. Zero free energy, because why assigned? Why? Any justification? That because Tm melting point of B is less than T1 and melting point of A is greater than T1. Okay. greater than T1. Okay. Next is what? This should there should be this is okay. GA0 liquid. Now GA0 solid is 0, so GA0 liquid will be greater than that and placed here. Okay. Look at here, placed here GA0 liquid. So that is mentioned here. GA0 liquid which is greater than GA0 solid GA0 solid is positioned suitably. Yeah, okay, should be better suitably. In this system, there is no scope of G solid solution. G solid solution because A solid and B solid are mutually immiscible. So they are pure. They appear as pure actually. Are mutually immiscible. Oh, sorry. And form no solid solution. They will form no solid solution. The next step is AB2. What is the free energy of AB2? So the standard free energy, you follow this. Write down this. The standard free energy of AB2 solid. You have to give the free energy of containing phases in the diagram. If it is alpha, G alpha. If it is beta, there G beta. Liquid, G liquid. If it is pure air, the GA0 here. Like this. If B solid appears actually, so B solid will not appear at this temperature. Okay. So if it appear, then we have to consider that free energy of B solid like this. Okay. So since AB2 appears, so G0 AB2, and that is actually a little tricky thing. It will be tricky. AB2 this I will explain. The standard free energy of standard molar. Remember, this is integral molar over 1 mole. 1 mole we are considering. Every delta GM, this is over 1 mole, molar. Everything is molar for 1 mole. So standard molar free energy of AB2 solid is given by the the height Mn. See the Mn? I drop a vertical line of height Mn. See here, this to this Mn. These are this type of curves, but it is a compound, so it cannot move around. Move actually, outside the rigid composition. Fixed composition maybe 2/3 there. So only vertical line you can expect. But free energy all the same. But how will you know this? Free energy, that means this height actually will be decided by the free energy or vice versa, or the standard molar free energy of this will decide the vertical height. Because we will draw tangent there, so this height is very important. So this standard molar free energy of AB2 is important. Then you have to draw. See, in the two-phase regime, AB2 appears. Liquid plus AB2. Liquid plus AB2 means two-phase means common tangent. So tangent to that. Liquid no problem, but AB2. So vertical line you have to draw correctly. So given by the height Nn. Height and is represented as follows. Achha. This one I am writing once more. Start phrase actually, phrase, yeah. AB2 phrase. So remove all this. AB2 just phrase. Okay, I wasted some minutes, but after this, give a star here. Start here. From AB2 is a, as if, since it is important, a little bit. Here what is P prime. What I wrote at P prime. What I wrote at P prime? I wrote what? At P prime. I have already written this. Okay, now start AB2 episode. Okay, AB2 about AB2. Okay, as I am writing here about AB2. This section. Okay, let us see. The standard molar free energy of AB2 solid is given by the height Mn in joule per mole. Remember, molar joule per mole. This is a question. Okay. Given by the height. I'm sorry. I'm coming to this. अच्छा, joule per mole and is represented as follows. Okay, 1/3 A solid plus, see, I'm using A solid plus 2/3 B liquid is 1/3 AB2 solid. This I am considering. AB2. This reaction I am considering. This is of course AB reaction leading to formation of AB2. A and B reacting to form AB2. So 1/3 this way I am writing. Okay, 1/3 is say call it equation 1. What I say right here, see follow. 1/3 mole. It is how many mole? 2/3 mole. If it were a solution, 1 mole how we get? XA mole, XB mole. XA moles of A, XB moles of B. Then total is XA plus XB means 1 mole. If you wanted say Na moles of A and Nb moles of B, then it will be Na plus Nb moles of AB solution. That is actually we say extensive property. But when it is 1 mole, intensive property. Come back to the 1 mole, molar, 1/3, 2/3 leads to 1 mole. Looks like 1/3. But here you have to apply your concept of solution. How many moles? 1/3, 2/3 will give you 1 mole. So 1/3 AB2 is equivalent to 1 mole. As if in terms of solution it is 1 mole. You have 2 moles, 2 gram atom and 1 gram atom, 3 gram atom. 1/3 of 3 is 1. This you can consider gram atom or gram mole. Same here. Okay. So I'm very sorry. Thank you. 2/3. So this you write what? This you write 1 effectively. Effectively 1 mole of AB stoichiometric solution. This you have to consider that this is as if solution making. It is a solution. AB2 is a kind of solution. What type of solution? Stoichiometric solution. A rigid, a compound, a rigid composition. What is that rigid composition? XB is how much? 2/3. But solution is actually flexible. When the composition can be flexible, can vary, then you speak of solution. But when this flexibility is removed, is absent, then it is a compound. So compound is a form of solution, a stoichiometric solution. So in that case 1/3 mole and 2/3 gives rise to 1. So it is 1. Why 1 we insist? Because we will find molar. So for 1 mole it will be bad if we draw the line for 3 moles or 2 moles. While everything else is 1 mole, this is molar. So it is all more integral molar. So how can we consider 3 moles or 2 moles or any number of moles other than 1 mole in case of AB2? So you write this way. If you wrote 3 times say A plus 2B goes to AB2, that AB2 will be equivalent to 3 moles. Right? I'm cancelling this. If you write this A plus 2 is AB2, it will not be 1 mole. In terms of considering the equivalence with solution, 1 mole and 2 mole, 3 mole. 3 mole of AB solution, but rigid stoichiometric solution. So that's why what we have divided by 3. So 3 is actually effectively 3. So divide by 3, 3 divided by 3, divide by 3. So 1/3 A plus 2. This is the reason. Is okay? If you have followed this, very good. Otherwise, let us proceed on at least. Proceed. Okay, this part is okay. This is equation number 1, remember. So, okay, very good. Keep on. You are focused on finding the value of ml, this height. How much you should to what extent you should drop the line, then you will be actually correct and thermodynamically correct, because you have to draw the common tangent. So this point, this main point will be very important. You will start from here. Okay. So don't worry. And A solid plus B, why not A liquid, B liquid? That I consider, because we have an advantage considering A solid and B solid. Free energy of these gentlemen will be 0, because we have assigned 0 for A solid, and 1/3 of 0 is 0. 2/3 of 0, B liquid is 0. So great advantage you will see. So change in free energy of this is nothing but the free energy of this. We are gradually moving towards finding the value of Mn. You see how you follow this. Very interesting, this segment. Okay. So the question is, how to find the height Mn in joule per mole. In joule per mole. Time?
1 hour 46 minutes gone.
Okay.
47.
Joule per mole. Note first that GA0 solid is 0. Already, and GB0 liquid is 0. Assigned values. Hence delta G01 is 1/3 G0 AB2 solid minus 1/3 G0 products minus reactants, delta G0. So at standard state, G0 is solid minus 2/3. See, right in bracket is a plus 2 products together, GB0 liquid. What is this? These are 0. So what remains? Is right here is 1/3 G0 AB2 solid. This is one mole, effectively 1 mole. So this is your molar. This is height Mn. 1/3 G0 AB2 solid is height Mn. Write nicely, height M. Okay, this part is okay in joule per mole. Now delta G. Now remove this. Wait a minute. Sorry, I'm just. Like this. So clean up this place. Now continue. This is the questions, okay? Delta G01, just find delta G01 and get height Mn, okay? Delta G01, okay? So this is molar, that's why it is height Mn. We want free energy for 1 mole, that will correspond, that will represent the Mn. Mn will be in accordance with that 1 mole. So this is height Mn. So what it is? Starting delta G01, finding delta G01. Little bit of manipulation, you are used to this, no problem. So you can find this. Okay, before this, let us quickly. Now delta G0, remember, just your job is to find delta G01. Now delta G01, delta G01 can be found if we can determine the delta G0 value for the following reaction. Okay, what is this? What is the following reaction? A liquid plus 2B liquid goes to AB2 liquid, AB2 solid, AB2 solid 2. This is 1. See how we are moving from A liquid plus 2B liquid goes to AB2 liquid. There's certain advantage of considering this liquid. See, we follow this. We will reach this equation 1. How? You consider this. A liquid plus 2B liquid is AB2 solid. Solid is unchanged, but here A solid has been A liquid here, and moreover 1/3 is not there. Just 1. And 2/3 not there too. Okay. So delta G0, call it equation 2. Delta G02 is obtained from K2 as what? As delta G02 is nothing but minus R T is T1 here, ln K T1 2 or K2. Okay, it's the same temperature, K2, then K2. K2. K2, where K2 is you write better write here. K2 as you write and assign temperature T1 temperature, because K is a function of temperature always. So you write here also K2 T1. Not bad, it is bad, not good. Yes, good it is, okay. Delta G0. I said that's what T1 I have used. This is K2 T1. Since these diagrams are all for temperature T1 and T is T1, this I will use now. This you will use. K2 T1 is, or you can use your concept, the same thing. K2 T1 is what? Where K2 T1 is what? Tell me. Right? Equilibrium constant expression, you know. Activity of AB2 solid by activity of A liquid, activity of B liquid squared, okay. Call it equation 3. Now this is okay, very good. This is okay, this there, okay. Remember, this is actually at equilibrium. So you have to refer to the equilibrium diagram, phase diagram, equilibrium diagram here. Let us see what we do now. Let us see. If we look at the activity versus composition diagram, in figure 3C, like this one, figure 3C, where AB liquid and A liquid are plotted against XB, or you may call it all XA as you like, XB or XA, in the composition range CD. In the composition range C to D. Consider C to D. See here. C to D. Here C to D where? C to D. C to D. C to D. C to D. See the phase diagram. C to D, which is this liquid is in equilibrium with liquid plus AB2. So liquid is in equilibrium with AB2. Follow me. Liquid is, follow me. C to D. What is this? Equilibrium with liquid plus AB2. Okay? This is phase diagram. So liquid plus AB2 at the temperature, liquid plus AB2 mixture. Oh, by the way, one thing I have missed actually, maybe, or I have not missed actually. No. At the end I will summarize this about this common tangents. Okay, once MN is drawing is over correctly in this okay, this vertical line is dropped correct precisely, then you will have the common tangent drawing comes later to show the coexistence of AB2 and liquid, with the liquid curve, and this at the foot of this MN means at the end point. This is the tangent. This I will explain. This I will discuss at the end. But let me finish how to find Mn. Okay, this is the question. How to find the height Mn in joules per mole. So in the composition CD, follow me. Liquid plus AB2. This is very interesting. AB2 solid is in equilibrium with liquid. In the liquid, who are present? Liquid who are present? Liquid is made up of who? Who and who? A and B. So A liquid and B liquid. Liquid means AB solution, liquid solution. A in the liquid form, impure though, because they are the solution. A liquid and B liquid in equilibrium with AB2 means this, we are actually following this equilibrium. So to find the equilibrium constant, we can take help of the activities values from here. Activity of a liquid, so the liquid of which composition? This composition of what activity? Since very easy, since it is actually for our convenience, maybe to our advantage, this is the ideal solution. So activity of A and activity of B would be actually their mole fractions. So this will be the answer actually. So so here repeat here. This only CD you consider. It later on I will tell you BC also can be considered. BC also liquid plus AB2. We consider CD first. Don't actually take undue pressure. CD liquid plus AB2. AB2 solid. Liquid plus AB2 solid. AB2 solid. These liquid contains A and B. So A liquid and B liquid. In equilibrium with AB2, you may write in this form. So in the equilibrium constant, we will find activities from the diagram. This is the activity composition diagram. Also, we know beforehand. This is not big deal. We know what is the activity. The activity is mole fraction, and mole fractions are all given here. The phase diagram itself. So let us see in the composition range CD, liquid plus AB2 coexist. Liquid plus AB2 solid coexist. Coexist means here liquid and AB2. Liquid and AB2 solid coexist. And it's plus. Okay. So hence the liquid phase is made up of A and B and of composition
2 hours 2 minutes gone.
Oh, achha. And let us see how long it can go.
How much more? 5 minutes?
No, 5 minutes. 10 minutes maybe. Let us see. Is this okay too? These are all intact too.
This is okay. Let me see that.
Fast.
Yeah, okay.
And of composition and of composition given by point D. Clear. Point D is clear. Liquid composition. This D. D. Liquid composition. You consider A and B. What is the XB here? You might say this is a D, sir. D is the value. What is the XA? D is what? XB. XB is the D. Composition means mole fraction. What is the XA? 1 minus D. No problem. These are composition mole fraction. What is the activity? Well, sir, activity is mole fraction because ideal solution. So this is D and this is 1 minus. This is D. D square. This is 1 minus D. This will be coming. This will soon coming. Okay, let us see. D square 1 minus D. And what is this? Activity AB2 solid. That is pure solid. And pure solid with respect to we consider pure solid as a standard state. This one there is no change in standard state. So pure solid with respect to we consider commonly it's pure. We consider with respect to solid. That is quite natural. That is actually implied here. Solid standard state. So on. So this is the K2. This is so this we get. This we get means what? Delta D02 we get. From this delta D02 we get, and once we get delta D02, then how to get to delta D01, which is the height Mn, that is a little bit of twisting, manipulation, which you know very well, how to reach from this to that. If you ask me, I will see the AB2 solid, no change. Oh, first of all, it is 1/3. This is only 1. So I will get multiplied by 1/3, etc., 1/3. And then what? Liquid, and this is solid. So it is 1/3 a liquid, 1/3 a solid. Liquid to solid, change in data, melting point, free energy data, available in the data book. So no problem. Given by point D, so this I will discuss. Is in equilibrium with AB2 solid. So liquid at the composition given by D is given by point D is in equilibrium with AB2 solid. Okay, this will actually exploit this information. Okay, we will utilize this. Okay, the values of AAL and ABL in equation 3. In equation 3, are XAL. What is AAL? Is XAL and XBL. What is ABL? XBL, Raoult's law, ideal solution. XBL, XAL, actually respectively. Since the solution, since the liquid phase is an ideal solution, since the liquid phase is an ideal solution, hence from equation 3, now start from this point with double star. I think we don't need this. Okay, we are interested here. This is our answer. Delta G0 1. Oh, sorry. Delta G0 1. This 1 has to be saved. I am writing 1 somewhere. Then I will get some lines. So let us start working here from this point. Hence, from equation 3, equation 1 I am writing. 1/3, I am repeating this, then I will remove this. I will get some space. 1/3 A solid plus 2/3 B liquid goes to 1/3 AB2 solid is 1/3 AB2 solid. This is known as equation 1. Saved. So this I am actually removing. You don't need. These are enough space. Anytime I want to refer to this, I will refer to that. Quickly. Hence from equation 3 start. Hence from equation 3. Hence from equation 3. Follow here. Equation 3 start. K2 K2T1 cell, write this, K2T1 is activity of AB2 solid, write once more, solid by XA, as I have already told you, XA liquid times XB square liquid. What is this value? You know, pure solid, 1 activity with respect to pure solid as a standard state is what? 1 by, what is XBL? XBL, see, XBL here, point D. What is the XB of the, in the liquid phase? In the liquid at point D, liquid composition is point D. Liquid and AB2. Liquid has the composition D. What is the XB then? D. D is the composition here, D. The XB is D square. And XA is what? Let's write another line, 1 minus XB into XB square. One minus XB liquid, right? XB liquid times XB liquid square. What is this? 1 by, oh sorry, what is this? Right here, continue here. Is 1 by, what is this? 1 minus, this is D square, 1 minus D. This is the answer. This is the K2. Okay. Alternatively, I am writing here. If you consider BC, you think yourself BC possible. B here, the liquid is of composition B. Composition B with equilibrium with AB2. Same way. Instead of composition D, liquid of composition D, it is liquid of composition B. Same way. So what you will get in bracket, you know. In that case, what it will be? What is the composition of XB is how much? Of B is the B. Is the B. That's why it is named B. B is the XB. So here XB is B is what? What it will be? And XA is 1 minus XB. So 1 minus
2 hours 12 minutes gone.
Achha, let's take a look. Yeah. It is gone.
No, still there.
2 minutes, okay, 2-3 minutes.
2-3 minutes.
1 minus B times B square also from where is also, if we consider same result. If we consider the composition range BC, composition range BC, B here to here, liquid plus AB2, liquid of composition B instead of composition D. So in the composition of BC, in the same manner, in the same manner. Happy? Okay? In the same manner, okay? So this is additional talk here. This is answer already. So K2, yeah, now what back? K2 means, now you know very well what is this? Delta G02 is known. Okay, so write back. Now, since the AB liquid versus XB plot is an experiment. This is an experimental plot. Experimental, is an experimental plot from both experimental plot. One can find K2 T1. I am always attaching equilibrium constant is the function of temperature. K2 T1 by using the experiment, by using experimental results into equation 4. So give this a name of this equation. Equation 4 here. Here is also this equation 4.
2 hours 15 minutes.
It's almost here and here. Just this much. Yes, this much. The main thing will be over. By using the experimental results into equation 4, this is equation 4, into equation 4, already have got this 1 minus d etc. etc. into equation 4, which gives this one, which gives delta G0 2 is minus R K2 T1. Actually delta G0 2, this is delta G0 2, you can write here also T1. Delta G0 is also a function of temperature. Write T1 here also and this to T1. Since T1 is our temperature of interest, so that's right. Is okay. So you have got what? Everything is about temperature T1. So I can omit this also, but you should note this. So what is this? How to get delta G01 now? Delta G2. The next question is what? These steps. Remember, delta G01, this one is actually the height ml. Remember, delta G01, one is height ml. This I will remove this now. Okay, height. These steps leading from delta G02 to delta G01. Delta G01 are as follows. What is this? How will you get this? 1/3. So you have already obtained 1/3 A liquid plus 2/3 B liquid goes to 1/3 AB2 solid is what? How much? AB2 solid. Delta G is known as what? What is this? See here. A liquid plus 2 liquid is what? 1/3. See, delta G02 you have is 1/3 delta G02. 1/3 is delta G. For this, delta G, general delta G is what? 1/3 delta G02. This 300 change is 1/3 delta G02. Is okay? You need to reach delta G01, which is this. How will you reach this? What is the difference between this and that? 1/3 why? It is 1/3 why? Delta G2 is what for? What is the delta G2? See, before I remove, see, what I have written? 1/3, 2/3. It is 1 and 2. Otherwise same. Liquid, A liquid, see A liquid plus 2B liquid. What is here? 1/3 A liquid plus 2/3 B liquid. Why I have written? So that it is in agreement with this. It comes close to this. Becomes same as this. So 1/3. So that's why I divide by 3. 1/3, 2/3. This is 1/3 AB2. When I do this, what is the delta G02? Delta G02. Since if you divide by 3, you know extensive property 1/3 delta G02. What is the delta G0? If it is delta G02 here, 1/3 of this, 1/3, 2/3, 1/3, 2/3, 1/3 is 1/3, 2/3, 1/3 is this. If we divide by 3, it will be what? 1/3 delta G02. So one step is forward and last is you reach here. You have to. So what's the difference? A liquid and A solid. That's it. So next is consider 1/3 A solid. On the left hand side goes to the right hand side 1/3 A liquid. What is this? Delta G is, in general, delta G is what? It is, tell me, known as what? Solid to liquid is known as melting. 1/3 1 third delta G0 melting, M for melting, A. Again you can give that temperature T1, okay, rate of melting, okay, rate of melting, A melting, M for melting, right here, A melting, just write full, melting is over, known, where you will get this data, data book, known for any data book, delta G melting, known from data book. From data book is over, so you combine last line, 1/3 cancel. See, you are reaching there. Remember, delta G0 will be the height of Mn. Remember, so delta, so you add this, 1/3 is solid plus 2/3, right, nicely. You are very close. 2/3 be liquid goes to 1/3 AB2 solid is nothing but this is the delta G is, this delta G is nothing but delta G, this nothing but 1 is already written there, delta G1 is variously known as what? Combination of these two, delta G1 is also height Mn, that is height Mn, your height Mn, keep on, is what? This is, remove this, you don't need anymore. This junk you remove. Height Mn is what? How you get this delta G? This one? By adding these two. So your right hand side you add 1/3 delta G02 plus 1/3 delta G0A melting. Melting A for A. So this is your last line. Box this. So this is how you are getting. This is what I am written. Height of Mn. What is height of Mn? Answer final. 1/3 delta G02, which I have already found here. This one. K2 and delta G0 is here. Delta G0 is minus Kn. K2 here. This delta G02 plus delta G melting from data book. So you get this. Thank you. So this height Mn, the drop, you got this. Then I will actually give you the, okay, the stability, okay, this tangentials, intercepts and common tangents and other things, okay, in the form of several points, actually, say 5-6 points, that is actually still remaining, but it is not fair to actually extend this class further. No, but this you have obtained the main things. That's remaining part next class. Remaining part. The remaining part next class. That is about this diagram. I will actually give you how you got this, okay, stability domains by through the relative positions of the G alpha and the relative values of positions of the free energy curves, okay, and the common tangent principle. Thank you very much with this. Okay, we have actually finished, okay, great extent of this topic, almost finished, but a couple of minutes I will take next class. Thank you very much for your patience and for your cooperation. See you next class. Bye.